Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 45. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with oscillatory transients are characterized by frequency, magnitude, and duration. Oscillatory transients, there are three types of frequencies. One is low frequency, whose pulse frequency is less than 5 kilohertz, and typical duration 0.3 to 50 milliseconds, and typical voltage magnitude is 0 to 4 per unit. Oscillatory transients of medium frequency is 5 to 500 kilohertz. Typical duration is 20 microseconds. Voltage 0 to 8 per unit. Number 3, oscillatory transients of high frequency, that is 0.5 to 5 megahertz, 5 microseconds duration, and voltage magnitude is of 0 to 4 per unit. As of the consequences of oscillatory transients, low frequency oscillatory transients have a primary frequency less than 5 kilohertz with the duration of from 0.3 to 50 milliseconds. Such type of transients is normally imposed on the electrical distribution systems, while the distribution utilities are going to switch on capacitor banks to improve their line power factor as well as to have lower system losses. At the time of transformer energization, the subsequent effect of the ferroresonance are also be the prime cause of occurrence. Occurrence, that is low frequency oscillatory transients. Ferroresonance or nonlinear resonance is thus to occur when a circuit containing a nonlinear inductance is fed from a source that has series capacitance and the circuit is subjected to a disturbance such as switching surges. The phenomenon of ferroresonance in power transformer can rather be characterized to have a typical situation where the nonlinear magnetic properties of transformer ferromagnetic core, while interact with the capacitance as exist at the connected electrical network, which has to produce a nonlinear tuned circuit with an unexpected resonant frequency. The inrush current that occurs when the transformer is initially made to turn on subject inrush current, while combined with the ferroresonance events, then there may have the possibility to saturate the transformer ferromagnetic core, and as of the subsequent effect leads to increase the injecting current significantly even under unloaded conditions. Back-to-back capacitors switching, transformer energization, ferroresonance would have been the usual source of concurrence. Low frequency oscillatory transients caused by capacitor bank switching. See the diagram. It has been concluded that the underneath happenings are the main source of disturbance as produced by the transient over voltages. A. Capacitor switching. B. Lightning. C. Load switching. Now see the points. Transient over voltages due to the switching of capacitor banks can be generated at low frequency or medium frequency. Transient over voltages due to load switching and lightning can be generated at high frequency. This will be the difference. That is, transient over voltages due to the switching of capacitor banks can be generated at low frequency or in medium frequency. But transient over voltages due to load switching and lightning can be generated at high frequency. In the system network, three types of electrical load components are actually made to function all through to draw both active and reactive power from the supply, and these are classified as resistive load, inductive load, and capacitive load. Resistive load is being the same effect on AC and DC network, but to perform the same function, it requires more current in AC than that of in DC. In resistive load, both voltage and current are in the same wave length with zero angle between them, and always has to act on the unity power factor. Again, I repeat, in resistive load, both voltage and current are in the same wavelength with zero angle between them and always has to act on the unity power factor. And inductive load, such as transformers, motors, etc., has the characteristics to convert current into a magnetic field. Inductive reactance that has to resist the change to current, causing the circuit current to lag the voltage. That's the difference between resistive and inductive. Inductive reactance that has to resist the change to current, causing the circuit current to lag the voltage. So, any inductive load once connected to the transmission line, the power factor that would have to lag because of lagging load current. Capacitive loads are opposite of inductive loads, which include energy stored in and absorb the capacitive reactance that has to resist the change in voltage wave, causing the circuit current to lead voltages. So, any capacitive load once connected to the transmission line, the power factor that would have to lead because of leading load current. Particularly in system network, the significance of capacitive loads are not so much prominent as compared to inductive and resistive loads. But these are becoming often prevalent as because of the constant deployment of complex type of electronics devices. As in the case of transmission line, it is perhaps to be noted that the line capacitance is inversely proportional to the distance between the conductors. Hence, the effect of capacitance that would have been less if the actual distance between the conductors conductors is configured to be more. For reactive power compensation and to provide effective voltage stability, most of the substations are thus to be equipped with capacitor banks. Extensive deployment of capacitor banks in substations that has not only improved the power quality but also made to increase the power transfer capability in the power system. Capacitor banks are mainly intended to reduce the phase difference between the voltage and current, and henceforth to act as power factor correction device in the power substations. Concept of flexible AC transmission system, which is called FACTS, flexible AC transmission system. The main objective to control the power flow in a AC transmission line is categorized by ensuring the underneath features. A, to enhance power transfer capacity and to modify power flow under the conditions subjected to disturbances such as sudden increase in load, line trip, or generator outage. And C, to ensure system stability and security. The stability can be affected by several problems, and that is to be exhibited during the incidence of low frequency power oscillations as due to generator rotor swings, loss of synchronism, and voltage collapse caused by major disturbances. In transmission network as a whole, quality of power supply can only be maintained by controlling the quality of voltage. Truly speaking, it has no control over the load currents. Throughout the length of the transmission line, the capacitance is assumed to be distributed uniformly, and for which would have to constitute the shunt parameter of the transmission line. As of the effect of capacitance, there exists a charging current in the transmission line which continues to exist even when the line is under no load condition or lightly loaded condition. Certain relevant points that has to determine the capacitance of a transmission line. One, the capacitance of a transmission line is directly proportional to the length of the line. However, the effect of capacitance that would be negligible if the length of the line is less than 100 km. The effect of capacitance would have become significantly high if the length of the line exceeds 100 km. The capacitance of the transmission line is inversely proportional to the distance between the conductors. If the distance between the conductors is more, the effect of capacitance will be less. And if the distance is less, the effect of capacitance will be more. The line conductor to earth capacitance depends on the clearance of the conductor with respect to the ground, which also affects the capacitance of the transmission line. If clearance of transmission line to earth would have been more, then the conductor to earth capacitance will obviously be less. the electric field intensity, that is volt per meter, is directly proportional to the capacitance of a transmission line. The electric field intensity, that is volt per meter, is directly proportional to the capacitance of a transmission line. To design extra high voltage, ultra high voltage transmission lines, the ground electric field intensity is on rather important factor, and its accurate measurement will play a critical guiding role. See the diagram, capacitance in transmission line. Three-phase line rather, RYB, line capacitance, and earth capacitance, that is the charging current flowing through the earth, to earth. The modern concept of implementing flexible AC transmission system facts, as in combination with the intensive application of compensation method, has explicitly made to provide better control of the active and reactive power flow in the transmission network independently of busbar voltage. Main objective of compensator is to modify the existing electrical characteristics of the transmission line to make it much more compatible with the prevailing load demand. Compensator will also be able to have a crucial alteration in the system power flow during any occurrence of sudden dynamic disturbances. Dynamic disturbances may have to initiate hazardous consequences such as transient oscillations. In such a situation, shunt compensator that has the ability to enhance the transient stability limit of the transmission lines and would have to provide an effective power oscillation damping on a priority basis as system conditions may require. In a power system network, there always tends to increase or decrease the voltage parameter at various buses as due to the usual complexity of the operational perspective. Reactive power dissipated by the reactive components, that is capacitances and inductances, would have to provide a predominant function of regulating the voltage parameter. Say, compensation techniques to control of voltage fluctuations. One is static compensation, another is dynamic compensations, or static compensators and dynamic compensators. Static compensators, that are one, shunt capacitor, shunt reactor, series capacitor. Dynamic compensators, synchronous condenser, synchronous inductor, synchronous phase modifier. Shunt capacitive compensation method. Any devices that have coils in them are inductive in nature. Inductive loads are being of much more complex, where the current and voltage are out of phase, and that leads to create a secondary voltage which has to move in opposite to the supply voltage. Transformers and transmission lines both have the characteristics to introduce inductance as well as resistance, and these parameters are always to oppose the flow of current. Once these two have connected to an inductive load, then the power factor would have to lag because of lagging load current. Basically, for the lagging power factor, the current lags behind the voltage, while for the leading power factor, the current is advanced in phase with respect to the voltage. For lagging power factor, the reactive component is thus to be negative. Whenever the power factor of the load is lagging, then it starts to absorb lagging reactive power, or can affirm that it delivers leading reactive power. Poor lagging power factor can be improved by adding a capacitive load in the circuit. To improve the power factor in the transmission system, steps should be taken to connect the line with a shunt capacitor, which has force to draw current leading to the source voltage. As the line capacitance of high voltage transmission line is always be high, so the line capacitance must have a significant role in voltage conditions of the receiving end. During the under voltage conditions, and to enhance the voltage at the receiving end, the shunt capacitors would have to be connected at the receiving end so as to generate and feed the reactive power to the load. That reactive power flow through the line has subsequently made to reduce the voltage drop in the line. To encounter the variable reactive power demands, requisite number of shunt capacitors are thus to be switched in the network or in the system. However, for implementing perfect adjustment of reactive power absorption, the transmission line that should always be equipped with well-knit design combination of the shunt capacitor and the shunt reactor. Shunt reactor. Shunt reactors are mostly used for two effective reasons. One, to limit or balance the transfer of reactive power in the network. Number two, to limit over voltages so as to contribute system voltage stability. As of condition A, in long high voltage power transmission lines, the conductors would have to act as a parallel plate of capacitor, where the air acts as a dielectric medium between the conductors. As on effect of the capacitance between line conductors and earth, there will be a generation of reactive power. Reactive power, while flows on the transmission system, would have to incur real power losses. Reactive power, while flows on the transmission system, would have to incur real power losses. Shunt reactors have the characteristics to absorb the reactive power. Absorption of reactive power that leads to improve the energy efficiency of the system. As of the condition B, voltage on an AC power system over long transmission lines is always be controlled by managing the supply and absorption of reactive power. A reactive current must have to be injected into the line to maintain within a range of voltages, that is plus minus 5% of the nominal voltage, by varying the shunt impedance. Shunt reactor is thus to be added as shunt inductive compensation, whose application is mostly needed either during the process of charging the transmission line at no load condition, or at the condition when the receiving end is thereby insignificantly loaded, that is lightly loaded, while the receiving end is at low load or no load. Then the voltage would have to increase along the transmission line, as because there is a flow of very low current through the line. It is important to conclude that a lightly loaded, very long overhead AC power transmission line may have a receiving end voltage higher than the sending end voltage due to the interaction effect between the inductance and capacitance of the transmission line. Over long transmission lines, the capacitance is therefore to be distributed along the whole length of the line. Once the voltage is applied at the sending end, then the capacitive load on the transmission line has the effect to rise the charging current, which also flows in the transmission line along with load current. A long transmission line has the usual characteristics to draw a substantial quantity of charging current. The charging current is leading in nature, while the load is lagging in nature, and both are opposite to each other. Subsequently, these two would have to cancel each other's effect, causing a decrease in the resultant current magnitude. If there would have been at no load or light load connected to the receiving end an increase in charging current, that would decrease the available capacity for the load current to flow. As of the consequential effect, the voltage at the receiving end is quite large as compared to the constant voltage at the sending end. Such voltage complications is of the effect called Ferranti effect, as because the phenomenon was discovered by electrical engineer Sebastian Gianni di Ferranti in the year 1887 during the installation of 10 kV AC based distribution systems in Great Britain. It is thus to be concluded that the capacitive loads would have to produce undesirable overvoltage stress on the primary side of the transformers connected at the receiving end of the transmission system, and due to have the Ferranti effect. Charging current, as it is reactive in nature, so the reactive power in the system would have been increased with the increase of charging current. But because of no load or light load connected to receiving end, the absorption of reactive power from the system would also be less, and that invariably leads to voltage instability in the system. To absorb this excess reactive power from the transmission line, the provision of shunt reactors should usually be at load end, which are to be arranged between the line and ground. However, in case of extra high voltage overhead lines, shunt reactors would have to be connected at both ends of the EHV line, as because there must have some usual uncertainty so as to which line end would be first energized or de-energized. One circuit breaker at each end is thus to be configured in the system to promptly switch in and out of these reactors. See the diagram. Equivalent impedance pi model circuit diagram of long extra high voltage transmission line, including switched shunt reactors at two ends. Here G is the generator, 52 is the circuit breaker, Z is the line impedance, Y is the admittance. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestion or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.